Okay, so in this journal here, we're going to be first figuring out if I give you a function. So f of x is another way we can write y, where x is an input and y is the output, or f of x is the output. So the function here is x to the third power, x cubed, and it says find the following values for the function. So here, what it says is like, what is the function if you plug in 3? So what is f of 3? So x here is, the 3 here is our x, and we're plugging 3 into this x and then cubing it. So we're asking ourselves, what is 3 to the third power? Well, that's like saying 3 times 3 times 3. Well, 3 times 3 is 9, times another 3 is 27. So in this case, this answer here is 27. If I were to try it out with this one here, well, this is saying what's negative 3 cubed. So we're taking this negative 3 and we are cubing it. So we have to figure out what's negative 3 times negative 3 times negative 3. Well, if I multiply these two, I get positive 9 times another negative 3 is negative 27. So in this case, negative 3 cubed is negative 27. And that's my values. So the reason why we're doing these problems is because, one, today we're going to figure out what does this x cubed look like on a graph. But before we can get there, I want you guys to realize that, well, when your x here is a positive and you plug it into an x cubed, you're always going to receive a positive number. However, when you have an x that's a negative number and you plug it into your x cubed, you're always going to get a negative number because there are an odd number of negative numbers. So like back when we had x squares, so if you have an x square function, when you plug in a positive number like 2 and you square it, you get positive 4. And if you plug in a negative 2, well, negative 2 squared is like negative 2 times negative 2. You're still going to get a positive number. So when you have an even power, you have an even amount of negative numbers being multiplied. So that causes it to be always positive. When you have an odd number as an exponent, you're going to actually get whatever sign you plug in. So if you plug in a positive, you get back a positive. You plug in a negative, you get back a negative. So know that even will always produce a positive numbers. That's not the case with odd exponents. Okay, so let's go into how do we graph an x to the third power? So graphing this cubic function, well, we're going to start off with making a table because we don't know what this cubic function looks like. So we have to make a table so that we can get some coordinate points. So I'm going to choose some x values that I think would be good for us to look at. Some just relatively small numbers, but I'm going to choose some negatives, a 0, and some positives for us to plug in so we can get a good idea of what this looks like on a graph. So if I plug in a negative 2, it's kind of like what I did in the bell work. So I'm going to plug negative 2 in for my x. And so that's going to give me negative 2 cubed, which is like saying negative 2 times negative 2 times negative 2, 3 times basically, which gives me, well, negative 2 times negative 2 gives me a positive 4. Positive 4 times a negative 2 gives me a negative 8. And so looks like when I plug in a negative 2 and I cube it, I get a negative 8. If I plug in a negative 1 and cube it, I get a negative 1 because I'm multiplying negative 1 3 times with each other. If I take 0 and I cube it, well, that's like saying 0 times 0 times 0, which is 0. Anything that is a base of 0. So 0 raised to any power will always give you 0. 1 raised to the third power is like 1 times 1 times 1, which is 1. 2 to the third power, well, 2 times 2 times 2 gives me a positive 8. And so now we have some coordinates to work with. So I'm going to graph the first one, which is negative 2, negative 8. So on this coordinate system, negative 2 is here on the x-axis, down negative 8. So I need to extend my y-axis to negative 8, maybe this to positive 8. So if I were to graph this, it would be like down here. And then the next one's at negative 1, so negative 1, down 1. My next one here is 0, 0, so that's at the origin. And then I have another one, 1, 1, so 1, 1 is right here. and then 2, 8. 2, 8 is up here. So if I were to connect the dots from the origin, it looks like this one swings up, almost like it's like half of a parabola, but pointing up. And then this side looks like it's pointing down, like a half a parabola that's pointing down. All right, let's kind of take a look at what we've produced. This almost looks kind of like a squiggle, right? And there's many ways we can describe this, but unfortunately there's no mathematical term to describe this shape. Most of the time I just call it the squiggle or the high five. It looks like if someone was raising a hand right here and putting down a hand. Some people think that this shape looks like a paper clip when it's unraveled. So there's many ways you can describe it, but most of the time I'll just call it a squiggle or like a snake shape. But this is what a cubic function looks like. So when I talk about a cubic function, it's this shape. One's pointing up, one's pointing down. And so there's one very important point on a cubic function. So just like a parabola where you have a middle section on a parabola being called the vertex, the middle part of this cubic function is what we call the inflection point. And the inflection point is the point where it's about to turn from, you know how like this point's pointing down and then afterwards it's pointing up? Well, this inflection point is where it's about to make that switch from pointing down to pointing up. All right, when it comes to x-intercepts and y-intercepts, if we look at the y-intercept here, it looks like it crosses the y-axis at 0, 0. And the x-intercept, well, it crosses the x-axis also at 0, 0. And the reason why for that is because we're looking at the parent function or the original graph for this function. So this here is what we refer to as the parent function for cubic graphs. And then another thing we want to mention is always domain and range. Domain talks about the x-axis. How far, or what are the x values that this graph produces? So notice how there is an arrow pointing to the left, right? And there's an arrow pointing to the right. So if this keeps on pointing to the left, it's going to keep going to negative infinity, right? So this is going to negative infinity. That way is going to positive infinity. So if you're going from negative infinity to positive infinity, this is going to be called all real numbers, right? And then the range, notice how it's pointing down and it's pointing up. So the lowest y value is going to be negative infinity. The highest y value is going to be positive infinity. So this is also negative infinity to positive infinity or all real numbers. In fact, all cubic functions, these types of functions here, the domain and the range will always be all real numbers. So when you get a problem that asks you for the domain or the range for a cubic, you can just write in all real numbers. Whereas parabolas, the only thing that is all real numbers is the domain. So in the next slide here, we're going to look at the phase shifts for certain cubic functions. So this, like I said, doesn't have any shifts. It's the parent function, so it's going to sit at the origin. But you can shift this right and left and up and down, and that changes the original function. So here I have an outline of a cubic function. Notice that this time around it is to the third power, and we're going to look at its different types of shift. But it's not any different from the different types of shifts of a parabola. So like, you know how these shifts help you find a vertex for a parabola? Well, in this case, these shifts will help us find the inflection point. So H and K represents the numbers that would help us find the inflection point. So if you have like a minus sign on the inside, this is attached to the X. So this tells us the shift for the horizontal shift. If you have a minus sign, you're going to be going right. If you have a positive sign, it's the opposite way, so left. If you have a plus sign on the outside, this is going to be up. If you have a minus sign on the outside, it's going down. And then if you've plotted your inflection points, cubic functions also need 3 points to make a full graph so that you can show that it's pointing up and down. So let me make a little note here. Cubic functions need 3 points on a graph. And so let's pretend that we've already plotted the inflection points. We need more points. And so that's when we go to the slope, technically the slope. So I'll put that in quotation marks because it's not really the slope, but you can use it as like you would use a slope. So your slope is the a, or whatever number is in front of the x, the constant in front of the x. And you have to make sure that it's always over 1. The slope's run is always over 1 because you can only use the slope one time from the inflection, okay? After that, you don't want to use it anymore. Same thing with parabolas. You only want to use the slope one time from the vertex, and then after that, you don't want to use it. The reason why is because parabolas and cubic functions don't gradually increase or decrease like a linear function, okay? They don't increase at a constant rate. Okay, so here are some problems from packet. So this is packet 6 on page 3. And I'm going to be working out 4 problems from the packet. So that was the end of the journal. If you want to figure out how to do some homework problems, keep on watching. So problem 1 here, I'm going to be looking at how to graph this cubic function. So let's start off with maybe answering a few of these questions like domain and range. So because I know this is a cubic functions, I know that the domain and range is going to be all real numbers. So I'm just going to fill that in. And then the inflection point here, well, I need to figure out the shifts. So if I have a minus sign on the inside, this is going to be right 3. Now on the outside, there's not like anything written outside of this parentheses, so that tells me there's no vertical shift. So I don't have to shift up and down. So we always start the origin, and this says right 3, so I have to go right 3, so that gets me to x equals 3. And so this coordinate point for the inflection is 3, 0. X here is 3, y here is 0. Now I need more points because I need 3 points total to make a cubic graph. So I start by getting the slope. The slope here is 1. So remember, the slope's run is always over 1. So I'm going to go from the inflection point up 1 over 1 and plot. And so when I, draw my curves, my squiggle, this side's going to curve up from the inflection point. But to do my other point here, I need to go down 1 and over to the left. So you have to actually go in the complete opposite. Because unlike parabolas where they're a complete reflection of each other, this is like the opposite direction. So that is pointing up, this is going to point down. So that's why we had to go down and then left, the complete opposite of going up and then right. And there we have our cubic graph. I do need to answer the y-intercept, but you'll notice that this curve doesn't touch the y-axis. So another way we can get the y-intercept is if we plug in 0 for x, because all y-intercepts, the x values are always 0, and then we have to find the y value. So if I grab my function here and I plug in 0 for x, I can work this out. So order of operations says parentheses, exponent, multiplication, division, adding, and subtraction. So parentheses first, so 0 minus 3 gives me negative 3. Exponents become next, and so negative 3 cubed gives me negative 27. Just multiply negative 3 times with each other. So in this case, my y-intercept is 0, negative 7, which is not so easy to graph on a coordinate plane. You would have to extend this to negative 27, which you could do, but we are not asked to do that. Here, we just need to calculate the y-intercept. All right, so let's take a look at the next problem. I'm going to be looking at problem number 3. So in this problem here, 3, I do need to start off with figuring out the shifts to figure out the inflection point. But first, let me fill in the domain and range since it's all real numbers. So the shift here, I have a plus 4, so this means right 4. And then I have a minus 1 on the outside, so this means down 1. So if I go right 4, down 1, that hits it right here. Oh, actually, I think I did this wrong. My bad. This should actually be left because it's a plus sign. So this is left 4. down 1. So I have to go this way and then down. So my inflection point looks like it's at -4, -1. And now for my y-intercept, well, actually, before I get to the y-intercept, I probably want the slope. So my slope here is -2, and so I can put that over 1. So -2 is my rise, so that means I have to go down 2 over 1 to the right and plot. And to get my other point, I have to go up 2 and then over to the left. So I'm going the complete opposite direction. So up 2 over to the left, and then I'm going to curve this down and then curve this up because I got to make that squiggle shape or that weird S shape. And so now I need to figure out my y-intercept. So we figure that out by plugging 0 in for our x and then finding our y. So if I plug this in, I'm going to need to work inside the parentheses first. So I have 0 plus 4, which is 4. And then exponent is next, so I have to take 4 and cube it, which gives me 64. If I take -2 and multiply it with 64, I get -128 minus 1, which is -129. And so it looks like my y-intercept is -129. And that would have been awful to graph because in that case, that number is ginormous. So I would have to go really far down my y-axis to graph that. So like I said, it's not asking you to graph the y-intercept. So I'm just going to write what my y-intercept is. Okay, so now let's take a look at our... So this one here is asking about graphing this problem, but it has a fraction outside, and that's going to change the way we need to figure out our slope. So before I get there, let's first write in our domain and range and find our inflection. So all real numbers for domain and range, because it's cubic. And then our inflection point, well, there's a +2, so that means left 2. And then up 1, because there's a +1. So if I go left 2, up 1, that's right here for the inflection. So that's -2, +1. And so I need my slope, which would be this point here. But here's the thing. Whenever you have a fraction as your slope, so this technically is -2 over 3 as my slope, but the run here is not 1, it's a 3. So to force this to put it over 1, what I'm going to do is change this fraction into a decimal. So when I do that, -2 over 3 is actually -0.66. Just take -2 and divide it by 3 and you get about 0.66, negative at least. When you change it to a decimal, you can put it over 1. And so that allows you to realize, well, I just have to go down 0.66 from the inflection point. So if I go down 0.66, that's about here. And then I have to go over 1. So then my coordinate point would be about right here. And then for the other way, I have to go up 0.66, so barely about 1 unit, and then over to the left, 1 unit. And then I'm going to curve this down and curve this up. And so there I have my cubic graph. Now I need the y-intercept, so I need to plug in 0 for my x. So this one I am going to be dealing with fractions, so one at a time. So inside the parentheses, I have 0 plus 2, which is 2, cube. 2 cubed is going to give me 8, because 2 times 2 times 2 gives me an 8. And then if I'm multiplying this fraction with a whole number, one way I can do it is just put the 8 over 1, and then multiply straight across. So -2 times 8 gives me -16. 3 times 1 gives me 3, plus 1. And so if I'm working this out, I can't add these two directly because this is not a fraction, so I can put this over 1 first, this 1 over 1. But then the denominators are not the same yet, so I have to multiply this 1 by 3 and the top by 3 if I decide to make the bottom a 1. I have to multiply the top by 1. So if I multiply this all together, I'm going to get -16 over 3 plus 3 over 3. And now since the denominators are the same, I can add the top. So negative 16 added with 3 gives me negative 13 over 3. And so there we have our y value. And you can also have done this using a decimal, that's fine. You would just have to have rounded, but I'm going to keep it as a fraction. All right, so in this problem here, this one's a little bit different from the rest because this one doesn't have a parentheses, right? But I want you to realize that if you look at the template for a cubic function, so I'll write what was in the the journal entry. Notice how the horizontal shift should be inside the 3, right? So if I were to ask you, okay, what does this minus 5 represent as a shift? Well, this is actually the vertical shift because it's not being cubed, okay? So notice that if it was a horizontal shift, it would have been inside a parentheses with this x, but it's not. So this is actually telling you the vertical shift. So this is saying down, because it's a minus 5, so down 5. Now, in this case, because there's not a parentheses here, there is no horizontal shift. In fact, this is like saying the same equation as x minus 0 to the third minus 5. Notice if you take x and subtract it by 0, you just get an x, and then you would cube it, and so this is the same equation. So there's no shift for the horizontal. So in this case, I'm just going down 5, which would be right about here. And so my inflection point is 0, negative 5. Now, if I really think about it, because this sits on the y-axis, this is also my y-intercept. So the inflection point happens to also be my y-intercept. Domain and range is all real numbers. And then using my slope, which is technically 1, it's a number in front of x, this is going to be 1 over 1, so I would have to go up 1 over 1, and then down 1 over to the left, the opposite direction. And then I would make my curves. And there we have our cubic graph. And that's it.